Hello, everyone, and welcome back to Laziness in Haskell. This is part 4, and today we are finally going to be facing our fears. We are going to address the elephant in the room, the subject that I have been very obviously avoiding for the first 3 parts of this series, which is quite intentional. But today we are going to be taking a look at thunks. This is going to be the thunk episode. So, I really wanted to present this series in a way that kind of provides a perspective of what laziness is all about, independent of thunks, because I really do see thunks as kind of an operational detail, and they're not inherent to laziness, but they are obviously an important aspect of laziness. So today we're going to devote this entire part to just talking about thunks, what they are, how they work, how they get introduced, and why GHC sometimes, it seems, introduces them a little bit more often than we would hope. So to start things off, I'd like to answer the simplest possible question, which is, what is a thunk? So the best way to think about thunks, I think, is actually as a slight variation on just an ordinary function. So let's talk about how functions work from the perspective of the runtime. So if we have some function that looks like this, it's going to be represented in memory in something that looks like this. So we have a pointer representing the function itself, and it points to a block of memory that contains the values that are closed over by the function. So in this case, that's just going to be z because x and y are arguments to the function. And then it has another pointer to a second block of memory. So why do we have these two different blocks of memory? Well, because this lower block of memory here is statically allocated. So what that means is that this is going to be compiled into your executable, and it's going to be shared for each evaluation of this lambda expression. If the lambda expression is evaluated multiple times, then the values that it closes over might be different, right? So we might have a different value for z, and that's why this block of memory here is heap allocated. It's dynamically allocated, so each time you evaluate this expression, you're going to get a fresh closure. But this pointer here is always going to point to the same block of static memory that says, I'm a function, here's my arity, and here's the code that you should run when it actually gets applied. Now, it might be a little surprising to some people that there's an arity in here, because in Haskell, all functions are curried. So shouldn't all functions have arity 1? Well, yes, from the perspective of the programmer, but in reality, that would be very inefficient. So GHC does actually represent functions as having sort of their preferred arity. And for this particular function, its preferred arity is going to be 2. Likewise, in this particular function, it just closes over this one variable z. So the only thing that gets stored in this local variable's payload is going to be z, or really a pointer to z. And then the code here is just going to be some code that pulls out, the arguments and this value out of this payload and then adds them together. It's just going to be some native assembly code. So this is how this function is represented, and as you can see, it's a pretty efficient representation. Each time this is evaluated, it's going to allocate 2 words on the heap, and that's going to be used to represent this function. Obviously, if a function doesn't close over anything, then it won't be represented on the heap at all, and it can just be, this block here can basically be statically allocated as well. The way that we represent functions in memory is more or less identical to the way that we represent thunks. The only difference is that thunks are a zero arity function. And this makes sense because if we have some expression that takes no arguments, then because Haskell is pure, it's always going to evaluate to the same thing. And so we can basically apply an optimization rather than just have an ordinary zero argument function. So what does that look like? Well, if we were to just have this expression and we wanted to delay it, then we could implement it as a thunk, which looks like this. And as you can see, it looks pretty much identical to what we had before. We have heap allocated block of memory that contains some local variables and a pointer. We lost the arity field because that's always going to be 0. And it says I'm a thunk, and then it has some code. Now, what's special about thunks and what distinguishes them from zero arity functions is that when we evaluate this thunk to get some value, then it would be silly, now that we've evaluated it once, to ever evaluate it again. So what we can essentially do is overwrite this closure here, this heap object, and we can say, well, now we're just going to replace the payload with just a pointer to this particular value, and we're going to overwrite this pointer here so that it just points at something that says I'm an indirection. Now, what is an indirection? Well, you can think of an indirection as just sort of a special type of thunk that always just returns the thing in its payload, right? It just doesn't do anything else than that. It's like a thunk representing a single variable. But of course, a thunk representing a single variable is very silly. So when the garbage collector sees something, a pointer to something that's an indirection, then it can take that pointer and just rewrite it to a pointer that points directly at the value. So it can shortcut this indirection step And this is very nice. This means that after, a single step of garbage collection, then these extra kind of wrappers all just get deleted, and we can really just think of a thunk as overwriting itself with its value. So why am I going into all these details? Well, I really want to emphasize the point that a thunk is represented in an identical way to a function. So we just have a pointer and then some values that closed over. So there is no difference between these two things, and there's not any fundamental reason to consider thunks as being somehow more expensive than functions. Now you might say, well, okay, but the process of updating it has a little bit of a cost, and that's technically true. But GDC has a very efficient implementation. It doesn't, for example, if the thunk is cheap, it's not going to do synchronization across threads to make sure that one thread is evaluating it. In fact, technically multiple threads could evaluate the same thunk, but that's totally fine because thunks will always evaluate to the same value, and that's not an issue. But in cases where we do have long-running thunks, then there's a process to basically make sure that one of those functions wins and the other one stops evaluating it and waits on the other one to finish so that we don't duplicate work. And this is a very nice trade-off. It's handled by the thread scheduler in the RTS, so the overhead is very, very low. So why do people have this impression that thunks are very expensive, but don't have this same impression that closures are very expensive? Well, the answer to that question is pretty simple, which is that the compiler automatically introduces thunks into your program, whereas it mostly doesn't do that for function closures. That's technically not entirely true, although I think these days it mostly is, because these days we have join points. It used to be the case that sometimes the compiler would introduce function closures into your program, but I think join points have mostly subsumed that. There might still be some cases where it introduces function closures, but it is certainly true that the compiler introduces thunks a lot more often than it introduces function closures. However, while that is true, I think that this is not always a pessimization. Thunks are not always a pessimization. Sometimes they can actually be an optimization, and therefore we shouldn't necessarily think of thunking as always being a bad thing. And in order to illustrate that, I'd like to return to the example from the very first video in this series. So to refresh your memory, we have this foo function. It takes 2 arguments. It has a loop, and inside of that loop, we have a function application applied to the loop variable, one that does not depend on the loop variable. And so we said, if this function is pure, then we can optimize things by just floating this out. And this is semantics preserving as long as this function is totally pure. But again, as we pointed out in Haskell, if this function has any possibility of bottoming, then this isn't totally pure, and it's not even necessarily a good optimization if this function turns out to be expensive, because if this loop is never evaluated, then we're going to be evaluating this function call even though this y value is never going to be needed. So what we could do is make things a little bit lazier, even in, say, an imperative language, by introducing some explicit lazy initialization. So we can introduce some variable that we use to keep track of whether we've initialized things so far, something like this. And then we can take this initialization here and push it inside of the loop. Now, this might seem a little bit silly because we floated this expression out and then just pushed it back in, and now we're doing this branch on every single iteration of the loop. And admittedly, it's true that if we actually had code like this, then the compiler would just rewrite this to float the conditional outside of the loop. But that's not really what I'm trying to focus on here. The point is that this is still actually an improvement over the original program, because this lazy initialization means that we are able to, without changing the semantics of our program, and without needlessly evaluating this, we're able to evaluate it just once, and then on subsequent iterations of the loop, the only cost that we pay is a single branch, and the branch predictor is going to be very happy with that. And so this is going to be a significant improvement in performance. But we did have to modify our program quite substantially because we weren't able to just float this out. We had to introduce this sort of lazy initialization here, which is a little bit verbose. And so often, even in imperative languages, we use data structures that abstract over this process. Often they're called promises or futures. Of course, these words mean different things in different languages, but the idea is that we have something like a thunk that starts out unevaluated, knows how to evaluate itself, and then overwrites itself. So given that, if we consider the Haskell version of this program, which here I'm just using a strict version of fold L, and we are just folding over this range of numbers, then once again, we can take this function here because it doesn't depend on anything in the arguments to the lambda, we can float it outside of the lambda. And this kind of illustrates how general this really is, because, this could be any higher order function. It doesn't have to be a loop. It could be map, it could be filter, anything along those lines. And we float this out and then refer to it inside the lambda. And without even having to do anything else, this is semantics preserving, because Haskell's lazy semantics mean that this is always a valid transformation, and this will just be evaluated if and only if it is actually needed. This transformation is known as the full laziness transformation, and it's always semantically valid, so GC can do it. And then, of course, it does have to pick how it's actually going to compile it. And one potential answer to that would be to just, leave the rest of the program structure the way it is and thunk this expression right here. But again, just as doing this kind of lazy initialization here was not a pessimization, it's an optimization, thunking in this particular case is generally an optimization. There is technically some, situations where it might not be an optimization. Like maybe this thunk ends up lasting a very long time and it closes over a bunch of stuff, and the stuff it closes over is really, really big. So, there can be pathological cases. But I would say that for the most part, in something like this, this is going to be quite nice. And if the thunk is not used, it'll just get immediately garbage collected. Another way of putting this is that the compiler has a bunch of tools in its toolbox, tools at its disposal, and some of those things are generating different code, and some of them are things that the runtime provides. And thunking is one of those tools. And in some situations, like this one, thunking is a very, very nice tool to have in the compiler's toolbox. However, I do think that, admittedly, when people talk about thunks being bad, they're not talking about examples like this. Instead, they're talking about examples where it really feels like the compiler, isn't gaining anything from thunking things, and it really shouldn't be thunking things. We don't want it to be thunking things, and yet it is. So let's take a look at a different example that perhaps illustrates that. So here I have a simple function that is written monadically, but it's not going to be written in IO. We're still just focusing on pure code for now. And this is just using some polymorphic monad that is capable of raising errors. So what we're going to do is take an integer argument. If it's positive, we're going to subtract 1 from it and then pass it to bar. And otherwise, we're going to throw an error in this monad. So if we assume that bar is strict, then we would definitely expect that GHC would evaluate x minus 1 strictly, because 100% of the time, this x minus 1 expression is going to be demanded if we've gotten to this part in the program. However, if you actually compile this function and you look at what GHC generates, you will learn that it thunks this expression. And this is very strange. This is very confusing. This seems kind of ridiculous, and it seems to totally fly in the face of what I was talking about in the previous video. If strictness analysis, if demand analysis can't even figure out this function, then surely it can't handle much more complex functions. But the answer in this particular case is that writing code in this style with a polymorphic monad is actually kind of uniquely good at defeating the demand analyzer. And it's very unfortunate that the style is used quite a bit. And in fact, I gave an entire talk on this specific thing 3 years ago at Zurihack 2020 called Effects for Less. I will put a link to it in the description if you want to kind of learn more about this in exquisite detail. But basically, if you're writing against a concrete monad, then bind can be inlined. But if you're writing against a polymorphic monad, or if you're using some kind of free monad or continuation monad that's going to be CPSing your entire program, then GHC is not able to determine how this is going to be used, because bind gets inserted in between each statement in a do block, and it just doesn't know what the bind is going to do. So it doesn't know if this is actually going to strictly demand this particular value here. Now, the good news is that this is kind of a uniquely common but also egregiously bad case, and I call it out specifically because this is sort of one of the standard ways that the strictness analyzer ends up getting defeated. But if you do write against a concrete monad, or you're not writing monadic code, you're not writing highly polymorphic code, or even if you are writing highly polymorphic code, but sort of the spine of your program is not highly polymorphic, then the demand analyzer works quite well, and it's able to understand the demand structure of your programs. But it's just something that, if you care about writing performant Haskell code, this is something that currently you have to worry about. However, it is the case that, even when people write code that is, very straight line Haskell code, monomorphic, they still find that thunks get introduced a little bit too often. So let's now take a look at an example that illustrates why that might happen. Here I have written a function that converts a color in the sRGB color space to its relative luminance, which is basically how bright it is. This is not going to be a video about color models, so I'm not going to go into the details about what this function actually does. The important detail for this video is that it takes a triple of 3 doubles and it returns a double. And it works by just doing some arithmetic basically on these doubles. It doesn't do anything particularly fancy, very, very simple computations. So I want to really dive into this particular function because it is going to serve as an example to illustrate some of the pathologies of the way that laziness currently works in Haskell. So let's start by actually taking a look at what code GHC generates for this function. So I'm going to pop into my terminal and I'm going to compile this module, enabling optimizations and passing a whole bunch of flags that basically just say, dump a bunch of debugging information out, dump out the intermediate representation. So I'm going to run this and then I'm going to look at what gets generated. And so this is the simplified core. So core is kind of the first intermediate language that GHC uses after Haskell. Haskell gets turned to core, core gets turned into STG, that gets turned to CMM, that gets turned into assembly. So core is the beginning of that pipeline, but most optimizations happen on core. So looking at the simplified core, the optimized core, is a very useful thing to do. And one of the things that we can immediately notice is that this function has had the worker wrapper transformation applied to it. Now, I actually made a previous video about the worker wrapper transformation, so I'm not going to go into it in great detail. I will put a link to that in the video description as well. But the important thing here is that the actual top level sRGB to luminance function doesn't do very much at all. What it's actually doing is just kind of unwrapping its arguments and then calling this $W sRGB to luminance function, which is the worker. And the important thing here is that the type signature has changed. And rather than taking a tuple and taking doubles, it now just takes 3 arguments, and the arguments themselves have this kind of hash at the end of them. And that means that this is an unboxed double. So rather than being a heap object, it's just going to be passed directly in registers, which is very, very nice. Now, looking at the actual body of this function, we can see that it's just, it's not very pretty, but it's just doing a bunch of arithmetic. And to kind of emphasize this particular point, I actually think it's more helpful to look at the intermediate representation one layer below this, which is STG. Because if we look at the STG here, you might look at this and you might say, well, this doesn't look like an improvement. But you can see that we just have case, 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 case. And what I really, really like about looking at STG code is that at the STG level, there's an invariant that case means we're just doing a strict evaluation and we're not doing any heap allocation. Whereas if we were doing some kind of heap allocation, whether to create some kind of, applying a data constructor or creating a function closure or creating a thunk, and that is represented as a let. So there's a very operational interpretation of case and let. And so here we can just see these long chains of just case, 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 no let to be seen. And so this is just going to end up turning into a sequence of instructions in assembly language that do a bunch of arithmetic. And obviously computers are very good at doing sequences of arithmetic. So this is very, very nice code gen. All right, so returning to the source code for this particular function, so far we have been looking at a case when everything goes right. So far, GHC has been able to look at this function, understand its demand structure, generate some very nice code. Everyone is happy. But what I now want to do is make a very minor change to this function. And so that we can compare them side by side, I'm just going to pull out this secret function that I had down here and look at them right next to each other. And again, this is not going to be a video about color models, but it turns out that luminance is the Y component in another color space called XYZ. So we're going to just generalize our sRGB to luminance function to a sRGB to XYZ function, which means that now in addition to taking 3 doubles, we're going to return 3 doubles. And the only change that I've made is that we're now returning this tuple, and this middle component, that Y component, is this expression right here. It's the exact same thing, but we've now added these 2 expressions above and below it for computing the X and the Z components. So otherwise, everything about the function completely identical. So we would expect that at this point, GHC should be able to generate code that is just as good as it generated before, surely, right? Because we haven't really changed anything at all. But if we go back and take a look at the code that gets generated now, we will find that something has gone terribly wrong. We are still unboxing the tuple. So we're still unboxing the tuples, the tuple in the argument, and we're also now unboxing the tuple in the result, which is kind of neat. But we're no longer unboxing the doubles themselves. We now just have doubles and not double hashes. And if we look at the STG code, things are even worse, because now we can see that gone is that nice case, 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 case code that we got before. Now we have a bunch of lets. And this sort of /u expression here, that represents a thunk. It's an updatable closure, and updatable closure, same as a thunk. So if we scroll through this, we can see that there's let. There's 6 lets here in this function that we get generated. So that's 6 thunks. So where do those thunks come from? Well, it's actually pretty easy to tell. LR, LG, LB, each of those things get thunked, and then each of the components of this tuple get thunked. And this is really troubling because, we've now just made a very minor modification to this program, and now all of a sudden we have completely destroyed the optimizations. So how can we make sense of this? Where are those thunks coming from? What about this modified version of the program is causing GHC to introduce a bunch of thunks? Well, the sort of immediate answer to that question is actually very straightforward. It's that tuples in Haskell are a lazy data structure, which means that when we have this expression down here that's constructing a tuple, it doesn't place a demand on any of its three arguments. And this is very important because when we consider the demand of a function, like basically what is demanded in a function by default without considering any of the internal demands, the answer is that any expression in tail position is going to be demanded by when we demand a call to that function. So in this particular case, the expression in tail position is this one, and this expression is strict in LR, LG, and LB, and therefore GHC is able to say, okay, these are all demanded, and that means that these function calls are all demanded, and this function basically always demands its argument because it uses it to branch, and that means that R, G, and B are all demanded, and so this function ends up being very strict. But if we look at the demand structure in this program, sadly, this is not the case, because here the only thing that gets demanded is this expression here, and because it's lazy in all three of its components, then nothing else is demanded. And so it ends up thunking each of these expressions, and then these expressions need to share the results of these expressions, so they get thunked, and this is important because we need to avoid evaluating R, G, and B in case they are bottoms. Because again, if we were to allow GHC to evaluate R, G, and B eagerly in this particular function, then we could end up changing a bottoming or a non-bottoming program into a bottoming one. And the reason for that is that technically speaking, it's possible to have a use site for this function where we call this function and we demand its result, but we don't even look at any of the three components, which of course is very silly, but it is technically possible. And because it's technically possible, GHC is not going to assume that any of these three things are demanded. Now, hopefully you are following everything that I just said, but even if you did, you might be feeling a little bit confused because in the last video, I basically said that, okay, but more laziness is good. And that's because more laziness gives the compiler more freedom to exploit the demand structure inherent in our program. But here what I'm basically saying is that in this case, laziness is bad. And we would get much better results if we were to introduce some of those artificial dependency edges. So in order to illustrate that that is in fact the case, let me add some bangs to these three definitions here. And, this is still technically not demanding these three expressions here, but it should be equivalent because these three expressions can never possibly bottom. So we would expect that, if these are demanded, then GHC will be perfectly happy to demand these as well. So let's test out that hypothesis and take a look at what we get. And indeed, we get very nice code gen where everything gets unboxed. We can go back over to the SCG and see that we just get case. So indeed, in this case, adding some additional demands do allow us to get back to that good code gen, but this is confusing because, again, in the previous video, I said that we don't want to add just a bunch of artificial demands because that would be ruining the demand structure in our program, and we want to allow the compiler to exploit that demand structure. So what's the difference here? Well, the obvious difference is that in this particular case, we don't actually know how this result is going to be demanded, right? We're just compiling this function in isolation, and we don't know how its result is going to be used. But what if we did know how its result was going to be used? What if we were to, uncomment this function and change it so that we're redefining it to just be defined in terms of sRGB to XYZ? Because after all, the luminance component is just the Y component here. So let's just delete the whole body and update it to be defined in terms of this other function. All right, so I've now done this. Let's now recompile and take a look at how this affects code generation. And unfortunately, what we find is that it's not going to be any better than not having this definition at all. We still find that the worker for sRGB to XYZ just has these box doubles, and it's still generating a bunch of thunks. If we look down through here, we're not, there's no specialized version of that or something like that being generated. We just have sRGB to luminance being a direct wrapper around this sRGB to XYZ worker function. So that's a little bit unsatisfying, but what if we made one very, very minor change to this program? What if we change this so that we no longer export sRGB to XYZ? Or it's the opposite of what I want. We no longer export this one. We do export sRGB to luminance. So again, not going to change any of the code, just going to change what is and is not exported, and we're going to recompile. And here, honestly, this is, I think, kind of cool. If we look at this program, we now find that we get exactly the same result that we had before when we had just defined sRGB to luminance directly. So now, basically, the sRGB to XYZ function is totally gone because, again, it's not needed anywhere. We're not even exporting it. And instead, it's been replaced by a version that is identical to what we wrote by hand. If we look at the STG code once again, it is also exactly the same. So this is kind of cool, and it does illustrate that in at least some cases, when GHC is able to understand the demand structure of our program, it is able to just kind of delete these expressions because it's allowed to do that. It doesn't have to evaluate them, and it's able to still generate very, very good code. But of course, this is very artificial. We're no longer exporting this function, which means we could have just written this by hand to just compute luminance. So this is obviously not a workable solution to things. So how do we make sense of this? Basically, what conclusions do we draw from this particular example? Well, basically what I'm trying to demonstrate is that even though theoretically there isn't a substantial difference between demands on arguments and demands on results, in practice there is a pretty substantial asymmetry between those two things. When we have demands on our arguments, the code that demands them is just right there, right? If we're analyzing the demand structures within a function, then it's very easy to see is R demanded, is G demanded, is B demanded, because they're only ever going to be demanded in exactly one place. We have sort of a closed world. These are the only ways that these particular values are ever going to be demanded. But when we have the demand on a result, we have to consider an open world, where there's always the possibility that even in some downstream package, somebody will define a new function that only demands the tuple wrapper and none of the components inside, no matter how unlikely that seems. So because of this, the only way that we could really get the same level of demand analysis of understanding the way that these individual fine-grained results are used in our function would be to do some kind of whole program compilation, where not just are we compiling sort of your whole application in one go, but you might have to compile your application and all of your dependencies in one go. Like a change in the application code might require recompiling all of your dependencies. And to be honest, I don't think that this is quite as ridiculous as it probably sounds, in the sense that you could imagine a kind of like, crank the optimizations all the way up to the maximum level, do some kind of two-pass compilation thing where you compile everything once to collect demand structures, and then maybe you go back and recompile everything, and you do this like once at the very, very end when you want just like the most optimal possible build of your program. But GHC certainly currently doesn't work like this, and I don't think GHC is going to work like this at any point in the near future. And to be honest, even if it did work like that, it's not clear to me that this would be straightforward, because we can imagine that this particular function might be demanded in lots of different ways. It might be that there's some use site that works like this, where we only demand this component. There might be some use site that demands all three, one that demands, these two, who knows? And this could generate an explosion of different demand structures for basically every single function in your program. And that could lead to a lot of code bloat, and it's not entirely clear how one would decide when it's really worth it. And of course, these are problems that already kind of exist with type class specialization. But I think, this might make it even more severe than it already is. Not clear to me how to do that reliably. So I think the takeaway here is that we have to practically treat the arguments to our functions and the results from our functions as kind of being demand analyzed in a different way. And the way that, I kind of like to think about it is that, again, demands originate from that expression in tail position, kind of percolate upwards through the function. And, this can mean basically, even if you have a function, you can do demand analysis on its arguments, and then things that get passed to that function in some other function, the demands can continue propagating upwards, but they don't really go the other way, right? We don't really have demands from the result of a function percolating into demands on its results. And so this creates kind of a directedness to our demand analysis process. And this is kind of a problem, because if we look at, a function even as simple as like safediv here, right? Safediv is going to be strict in this argument because it uses it immediately, but it's never going to be strict in x because of the fact that x is used inside of this just constructor. And to me, this is kind of absurd, actually. This is basically never what I want. Like maybe in rare cases, if I have some function that computes some complex thing and it returns nothing or just, and it turns out that, it's very cheap to compute whether or not it fails, and then it's very expensive to compute the actual value, then sure, I mean, it could be useful in some cases to be able to get the Boolean result of whether it's nothing or just without having to compute this value here. But I would say that that is very rare. And the vast majority of the time, when I'm adding a little bit of optionality to my function, I'm not asking the compiler to optimize for that case. I just want to add a little bit of optionality to my function, and I still want basically a demand on this result to be treated as also a demand on the value inside, because that's what's going to happen 99% of the time. So obviously it's possible to say add strict application here to express that, but this means that now every time I use the just constructor, I have to do that, and every time I use a pair constructor, I have to add bangs in places. And to be honest, that's a really bad default. I'm probably not going to do that. And if I do it completely mechanically, then I might even end up, making things too strict, because I'm not going to reason through every single case in every single program about where the demands really are and really aren't, and annotate things. Basically, this is an illustration that assuming that everything is maximally lazy is perhaps a bad default. But wait, isn't that completely contradictory with what I just said in the previous video? I'm now saying that assuming that everything is lazy by default is a bad default. In the previous video, I said that, the only alternative to that is assuming that everything is strict by default. And that's not a good default either. Well, again, there's sort of an asymmetry here, which is that when it comes to data types, right? When it comes to things that we're actually constructing, then those, I think it actually probably does make sense for them to be strict by default. Because in most cases, like in this example here, when I'm constructing something in the result, then I don't want to make a super fine-grained distinction between a demand on the overall value and a demand on just like a part of that value. But this is quite different from, wanting to place demands on sort of individual expressions or arguments to a function, because in those cases, then I do want the compiler to have freedom to move things around. Another way of thinking about this is that it's possible for the compiler within a given function to sort of push expressions down, because we want, if we're lazy, then that means that the compiler has the freedom to move expressions closer to where they're needed. And this could be the argument to a function, or it could be a case expression, or an if expression like it is here. But if we have just a result from a function, then there's no way for the compiler to move this result closer to where it's used, because where it's used is not in this function, right? And this is kind of as far down as it can push it. And so again, we have this asymmetry. And because of this particular fact, it's quite nice that GHC does now actually have a language extension called strict data, which basically does exactly this. It makes it so that every time you define a data type, whether that's a record or a sum, then all of the constructors are strict by default, but everything else is still lazy. And in my experience, this tends to provide a pretty nice practical trade-off, because it means that, again, when you construct something and return it, then you're sort of saying that's a sink for values. I want everything that ends up in there to be demanded. But within the given function, you give a lot of flexibility to GHC to rearrange things and move them around. So this is all very great, but admittedly there is kind of a lurking issue here, which I'm kind of not acknowledging, which is that all of the data types in base are lazy, basically. We have lazy tuples, we have lazy lists, we have lazy, obviously, maybe and either. And even if you enable strict data, it's not going to change those, because, well, those data types, people depend on their strictness being a particular way. And I do think that, unfortunately, this is a real limitation of the way that Haskell is currently put together. It's not really an issue with the language, but it is still, just because it's an issue with the standard library rather than the language proper, that's not a distinction that matters very much to most people. I do think, having said that, a lot of the time, the sort of costs of laziness, the costs of the expense of creating all these thunks is overstated. And perhaps in future videos, I'll go into even more detail about why I think that's the case. And I think that people tend to underestimate the extent to which memory usage in Haskell programs just comes from the fact that we use like really crappy data structures. Like the fact that we use simply linked lists to represent data at rest, that's a bad data structure, whether it is strict or lazy, but it is what we do. And that uses a lot of memory. But it is true that basically by having these really, really lazy data structures in base, we are sadly preventing GHC from doing nice things to our programs that I think generally we would like to be able to do. So using strict data, it helps a bit. This is still a real concern, and I don't have any great solutions to it, sadly. Now, at this point, I think I probably need to start wrapping things up before I really start rambling. I want to ramble just a little bit more. And specifically, I want to talk about the list data type, which I have intentionally avoided really talking about. I think a lot of the time when laziness is brought up in Haskell at all, the thing that comes to mind most often for people is list. And to be honest, I kind of get it, because I think that list is probably the only data type in base that actually has a good reason to be lazy. And I don't think that making list strict by default would be a good data type. And the reason for that is that a singly linked list is a terrible data structure for storing data at rest. But the purpose of list in Haskell is as this streaming data structure, which allows us to, convert between different data structures. It allows us to process things incrementally. It allows us to do list fusion, and that's really cool. And in fact, those sorts of things are so useful that you'll find them in imperative languages as well. So that is a useful data structure to have, but it doesn't really say all that much about laziness in Haskell. So I kind of explicitly want to not talk about those things and instead focus the conversation on data types like maybe and tuples and either, where I think the laziness is a lot harder to justify. All right, so with that disclaimer out of the way, I think it is time to start wrapping things up. And for this particular video, I would like to do that by providing a little recap of our story so far, because I know that this video is probably going to be a little bit more of a letdown, I think, for some people than the previous ones, because in the first 3 parts of the series, I've basically been saying, oh, laziness is so awesome, laziness is so great, Haskell is so cool. And this video is a little more gray, right? But I don't want to lose sight of the bigger picture here. And I intentionally chose to not talk about these things because I wanted to distinguish the things about laziness that are really, really great from kind of the implementation infelicities that make it maybe not as great as it should be in Haskell today. So let's go back and summarize what we've learned. Number 1, we want GHC to exploit the structure of our programs. I think if you disagree with this, then I guess I don't really know why you're writing Haskell, but intuitively it seems like GHC should be able to do this because we, write all of these pure expressions. But it turns out that bottoms make this complicated, and we kind of can't avoid bottoms. We kind of do need bottoms. So we need some semantics that allows us to predict which expressions will bottom and which ones won't, and we don't want the compiler to, break our programs in this respect. And so the semantics that seems to work really well for this is a lazy semantics, not a strict semantics. So laziness is good. Lazy semantics is something that we should be happy with. But in order for it to optimize our program in a good way and not, introduce these extraneous thunks, then we need to have a good demand structure. And we need to be able to communicate that good demand structure to the compiler so that GHC is able to understand which things need to be evaluated and which things should not. And in order for that to be, usable by your average programmer, then we need to have good defaults. And this is currently maybe, I think, the area where Haskell is kind of lacking. Maybe it falls down a bit, and I think that we can improve this. This is a solvable problem. I don't know exactly currently how we can fix it without breaking backwards compatibility, but we definitely should not throw everything else out and say, oh, laziness is too hard. It would be a real shame if we basically gave up on all these really nice things just because we have a bunch of overly lazy data structures in base. So this is basically the thesis that I've been building up to for the first 4 videos in this series, and I've basically delivered it now. It's done. I have communicated the core things that I wanted to communicate, but we're not quite done yet. There are some more things that I would like to talk about. I don't have quite as good a hook for the next couple of videos, but things will continue. It will just continue after a brief break because I will be out next week for ICFP. But there's still a bunch of things we haven't talked about. We haven't talked about how laziness interacts with I/O. We haven't talked about alternatives to laziness and strictness. There are some other semantics that people have proposed. We haven't taken a look at, ways that people have attempted to provide non-strict semantics or imprecise semantics in strict programming languages. So there's a bunch of things that I would still like to talk about that I think are very, very interesting and concern laziness. So I hope to see you in a couple weeks. And until then, see you next time.